Chemical reactions of analytes produce products that can be detected by using optical methods. Changes in light absorbed, scattered, or emitted by these products are used to determine the concentration of the analyte. In potentiometric methods, changes in concentration of ions are sensed as potential difference between two electrodes. Calibrator solutions of known concentration are used to establish the relationship between the magnitude of an optical or electrical signals and the corresponding concentration of analyte. Quantitation of routine chemistry analytes is typically based on one of two measurement principles: measurement of light, photometry or spectrophotometry, or measurement of electrochemical potential, potentiometry. There are many variations of photometry and potentiometry, but all have in common that the signals, the amount of light or electrical voltage is predictably related to the amount of analyte in solution. Electrical voltage is predictably related to the amount of analyte in solution. Photometry relies on measurement of light by photodetector. The light may be absorbed by substance dissolved in solution, absorbance. The light may be scattered or refracted by particles suspended in its solution, turbidimetry or nephelometry. The light may be emitted from substance that absorb light at one wavelength and emit light at another wavelength, fluorescence. Specific wavelengths of light are chosen for each analysis based on the properties of the substance being measured. A typical light source lamp generates a broad range of wavelengths of light. A visible lamp produces light of wavelengths from 400 nanometer violet light to 700 nanometer red light. An ultraviolet lamp produces light of wavelengths from about 200 to 400 nanometer. To select the desired wavelength from the spectrum of light produced by the light source, a device called a monochromator or a filter are used. A monochromator disperses the light much like a prism disperses light and allows selection of a narrow band of wavelength to be directed through the sample cuvette. Cuvette cell made of optically transparent material that contains solution for analysis by optical methods. Here the visible light from 400 to 700 nanometer. Absorbance: when an analyte has an intrinsic color or generate a color upon chemical reaction. Visible light is absorbed when it passes through a solution containing the analyte or reaction products. The selective absorbance of certain wavelengths of light from spectrum of white light gives the solution its color. For example, a solution containing hemoglobin appears red because light in the green range of spectrum wavelengths of 500-600 nanometers is selectively absorbed, removed from the white spectrum. Measuring the decrease in green light that occur upon passing through the solution gives an indication of the amount of hemoglobin present. Here, this figure shows the configuration used to measure light absorbed, the difference between emitted light from the source and the light reach the photodetector. Here the source and here the photodetector, the cuvette and this light source, here the photodetector. Compounds that have no visible color often absorb light in the ultraviolet region, and this absorbance can be used in the same way as absorbance of visible light. The specific wavelength of light chosen is based on the absorption properties of the compound being measured. As the amount of substance in solution increases, the relative amount of light that passes through the solution and reaches the detector decreases. The decrease in light is termed absorbance. A formula called Beer law describes the relationship between concentration of the absorbed light for a given metals A, E, L, C, where E is the extinction coefficient, L is the length of the cavity, C is concentration. Beer's law, the relationship between analyte concentration and the change in absorbance, turbidimetry, and nephelometry. Some tests are based on formation of insoluble particles that interfere with the passage of light through the solution. The analyte reacts with an added reagent to produce insoluble particles that remain suspended in the solution. When light hits these particles, some of it reflected in different directions. Higher concentration of analyte present a greater number of particles that will inhibit light passing through the solution and increase the amount of light reflected. It is possible to measure the loss of light passing straight through the solution called photometry, and the increase of light reflected in the different direction called nephelometry. In turbidimetry, the detector is placed in direct line with the incidence light, and the light sensed by the detector decreases as the number of analyte particles increases. In nephelometry, the detector is placed at angle In nephelometry, the detector is placed at an angle to the light path to avoid detection of the light passing through the sample. The nephelometric detector sends light scattered by the particle. The amount of light reaching the detector increases as the number of analyte particles increases. Often antibodies are used with these methods and represent a type of immunometric assay, specifically immunoturbidimetry and immunonephelometry. The antibodies in the reagent will cause analyte molecule to form complexes or lattice, and these large particle aggregate enhance the reflection of light, increasing the analytical signal that is measured. This is turbidimetry. The light source of it containing the suspended particle and the photodetector. Here nephelometry, light source and the cavity containing suspended particles. This the photodetector. Turbidimetric and nephelometric methods are often chosen to measure proteins such as transferrin or prealbumin, two important transport proteins in the blood. Proteins are relatively large molecules that can be easily cross-linked by selective antibody to produce aggregate particles that are the right size to reflect light in the visible or ultraviolet range. Some drugs of abuse test can quantitate the concentration of drug in patient sample by measuring the changes in turbidity. Due to the competition between drug in patient sample and drug bound to microparticles with antibodies added to the solution, fluorescence. Some drugs of abuse test can quantitate the concentration of drug in the patient sample by measuring the change in turbidity due to competition between drug in the patient sample and drug bound to microparticle with antibody added to the solution. Fluorescence. Certain kinds of chemical structure are able to absorb light of one wavelength and emit light of another wavelength. These substances are termed fluorescent compounds or fluorophore. In each case, the incident light is of shorter wavelength and higher energy than the emitted light, so a substance that absorbs blue light wavelength 400 nanometer may emit lower energy green light wavelength 500 nanometer. The detector is placed at 90-degree angle from the incidence light so that it detects only emitted light and not residual incident light that pass directly through the sample or reflected light bounded back from the sample or cavity. Incident light is a shorter wavelength than the emitted light, high energy, low energy. Analytes of interest in clinical chemistry are not innately fluorescent. Instead, fluorescent molecules are incorporated as reagents to help detect analytes. For example, immunological methods for measurement of tumor markers like CA125, ovarian cancer marker, or CA115-3, breast cancer marker, use antibodies that have fluorescent compound attached. The antibody recognizes and bind to the tumor marker. Excess unbound antibodies are washed away, and the amount of fluorescent light generated is in direct proportion to the amount of tumor marker in the sample. Chemiluminescence is light emission due to the chemical reaction. Similar fluorescence, there are some molecules that due to their structure can produce light rather than heat when they react with other molecules. Some immunological methods for measuring hormones and tumor marker utilize a chemiluminescent molecule. After selective antibody bind to analyte in the patient specimen, the bound and unbound antibody are separated, and a second antibody linked to chemiluminescent molecule is added. Once bound to the first antibody bound complex, a chemical is added to the mixture to generate chemiluminescent signal that is proportional to the amount of analyte in the sample. In a variation of this technique, the chemiluminescent signal is generated by pulsing the mixture with electrical current rather than through the chemical reaction. This method is called electrochemiluminescence. Electrochemiluminescence. Thank you.